Okay, so we just said that a derivative can actually be a function. So let's look at what this function would look like if we graphed it. So sketch and label the graph of the derivative function of the graph below. Okay, so here we have a linear function, which is great. And that means that the rate of change, or the derivative, is going to be a constant. So that rate of change at every x value is going to be 2 over 1, which is 2. So the derivative for all of this, that rate of change is constant. It's always going to be 2. So this would go through the line. So for any x value, so for any of these x's, the rate of change is always 2. So that's going to be a horizontal line that goes through. Y equals 2. So again, derivative function is the rate of change. So it's the change that's happening at each x value. At every x value, it's changing at the same rate at 2. All right, let's look at one that's not linear. So if I was looking at this, sketch and label the graph of the derivative function of the graph sketched below. Okay, so this is going to take a little bit of time, but that's okay. So if we have this, I'm just going to go through and I'm going to just choose some values to find some tangents and just kind of make some estimations. So let's just say I wanted to look at this value here, f of -4. So if I were to kind of rough sketch this out, I'll do this in like a green color so you can see the difference. So if I were to rough sketch this out, that tangent line, all right, I would say this is up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over 1. So I'd say the derivative at -4 is 10. So if this is my derivative function, when x is -4, your y value is 10. So I'm just going to put a point up there. All right, so let's look at what happens now when x is 3. -3, I mean. So when x is -3, if I were to draw, again, let's figure out what the derivative is there, just by rough guessing it. So I would say this is over 1, or up 1, 2, 3, over 1. So the derivative at -3 is 3. So at -3, I'm at 3. So again, all I'm doing is finding the value of that derivative at each specific y value. If I were looking at here, say I wanted to look at what happened when x is -2. If I were to draw that tangent line, I'm going to have a horizontal line. The slope of that line is, it rises 0, and it runs however much you want it to run, so it's going to be 0. So the derivative function at -2 is 0. Again, the rate of change of our function at -2 is 0. That's what that means. Okay, now let's go down here. Let's look at what happens at f of 0. Just draw kind of a tangent line there. So if I were to estimate this tangent line, I'd say over 1 down 3. So that slope is going to be rise over run, so -3 over 1, so -3. So f prime of 0, so at 0, the function is going down at a rate of 3. All right, let's use this next point here. At 2, we've got that horizontal line again, so that slope is 0. And then let's look at what's happening here at 3. Just draw a rough sketch of a tangent line. So for me, I'd look at this and say over 2, up 1, 2, 3, 4, 5, 6, 7, 8. So 8 over 2, which is about 4. So that's happening when x is 3. And then at x equals 4, this is going up crazy big. So we can kind of see the shape of this graph. Hopefully you can see this is a parabola. So again, all I did is I just took my function, my original function, and I found what the derivative was at specific x values, plotted those points, created the graph. So let's look at another one. Okay, so we can see here, as these x values are getting really, really, really small, so going towards negative infinity, we can see this is getting really, really close to 0. It's not quite 0, but it's getting really close to 0. So I could say the limit as x approaches negative infinity of the function is 0. So that means if I were to graph the derivative function, as your x values get really big, they're going to get closer and closer to 0. Okay, let's find some more points. So let's look at maybe this point right here, or let's look at 0. So if I were to graph the tangent there, I would say it's like that. So this would be, let's see, I've got a point here and a point here, so up 1 over 1, 2, 3, 4. So I'd say this is at about 1/4. So at 0, I'm at 1/4. All right, let's look at what happens right here at 2. So at 2, I graphed that tangent line right at 2. Okay, so this would be up 1, 2, 3, 4, 5 over 1. So at 2, I'm at about 5. And then it looks like I'm on that same slope here when I get to 4. I'm at that same slope that I was at 0. You can see that the line here and the line here is about the same, so I'm going to count those as the same. And then we can see here that the limit as your x values are getting closer to infinity of the function, your function is getting closer to 2. So that means as your x values get really, really big, your y values are going to 2. But when I go to actually look at what that looks like for the rate of change, you can see that rate of change is just going to be leveling off to 0. It's still, the rate's still going up, but it's getting slower and slower and slower. And if I created that tangent there, the tangent lines are just going to get, the slope of them are going to get closer and closer to 0. So this is going to be that same thing here. So again, if I was looking at it, I think I want to repeat how I kind of explained this. I think I explained a little bit off. So if I was looking at the slopes of these tangent lines here, you can see these are basically horizontal lines. So the slopes of those are 0. So this is going to be, they're not going to be exactly 0 because it's still a slanted line, but as we get further and further away, those horizontal lines start to become pretty, or those tangent lines start to become pretty horizontal, so they get closer and closer to 0.